In this video, I want to take a look at how we find a basis for the row space of a matrix and the null space of a matrix. And it really comes down to this. We're going to put things in row echelon form or reduced row echelon form. And that was going to show us what the basis is. And it's based on a couple of theorems here. One, elementary row operations do not change the null space of a matrix. I mean, this is sort of the basis of how we've been solving systems, right? We take a system, we make an augmented matrix, and we do row operations on it to create a new system that has a simpler to see solution. It's the same solution, but it's just easier to see, or easier to write down. And so for the null space, which is just the solution space of ax equals b, this is the way we've been doing it all quarter, right? We do row operations to find the solution space. Okay. But more so, elementary row operations don't change the row space of a matrix. Now remember, the row space is the set of linear it's the span of the rows, the set of linear combinations of the rows. And so think about there's three row operations. One of them is to swap two rows. Well, if you're taking a linear combination of all the rows and you swap two rows, you're still taking a linear combination of the same thing. I mean, addition is commutative, so whether you add two things in this order or in that order, it doesn't matter. So swapping rows doesn't change that. Multiplying a row by a constant, right? Well, if you take a row and you multiply it by a constant and think about the vector, and that row vector just gets longer. And so if you're taking linear combinations with the shorter version of the vector, well, I'm assuming I'm multiplying by a number bigger than 1, so it might be shorter if it's less than 1, but anyway. Before you alter the size, you're taking a linear combination with that, or after you alter the size, as long as you can scale it back to what you started with by dividing by that number you multiply by and then multiplying by the appropriate coefficient, you're still getting a linear combination of that vector, and you're not changing the space. It would matter if you were multiplying a row by 0. But in that elementary row operation, you're not allowed to multiply by 0. And the last row operation, is the least obvious as to why it doesn't change the span. But if you add a multiple of one row to another row, then that doesn't change the span. And the way I see that is that if you've got this new row that's the old row plus some multiple of another row, and you take a linear combination using that, so you're going to have a constant times the old row vector plus a constant times a new row vector, and then you distribute in, then you're still getting a combination of the old row vector and the other row vector that you added onto it, but that can be added onto the other thing that you've already added onto it. Anyway, it's still a combination of the same rows, just sort of lined up differently. So adding a row vector to another row vector, or a multiple of one row vector to another row vector, does not change the span. You're still spanning, it's taking linear combinations of the same things. And so what we're going to do is we're going to take a matrix and do row operations on it until it becomes more obvious what are the independent vectors, right? Because if I'm looking for a basis for the row space, I've already got a spanning set because all the rows together span the whole span. The definition is it's the span of the rows. Okay, so if all the rows together are not a basis, it means they're not independent. So I've got to see which ones are going to be thrown away. So here's an example here. Let's take this 4x5 matrix and put it into reduced row echelon form. So here it is in reduced row echelon form over there. The thing I notice here is that 2 of the rows went to zeros and 2 of the rows didn't. And in fact, those 2 rows that didn't, it is clear to me that they're independent. Because with only 2 being left, the dependency is one of them a scalar multiple of the other. And clearly this first row is not a scalar multiple of the second, or vice versa. Right? And so those are independent rows. I only did row operations to get from here to there. So my claim is that those 2 rows are a basis for the row space. Now, that doesn't mean that the first 2 rows here are a basis for the row space, because one of the row operations we might have done is we might have swapped rows around. So just because it's the top 2 rows doesn't mean it's the top 2 rows over there. right? I mean, it's possible. I mean, it's never going to be the case that you end up with zeros on the top and then stuff down the bottom. Like you're going to end up with the bottom two rows and not the top two rows, because in reduced row echelon form, the zeros are all at the bottom. So the independent rows float to the top is what happens, whether they were independent to start with or not. Okay. In this case, we've got these two rows. So a basis for the row space of this matrix that we started with is the same as the basis for the row space of this matrix. And this is clearly these two vectors. So these two vectors are also a basis for the row space of the original. In the next video, we'll actually see a way of getting actual rows to be part of the basis. But in this case, when we do it, we have to take the independent rows of the reduced matrix, not of the original matrix. Now, the process of finding the basis for the null space is one we've done before, because we've solved systems of linear equations, homogeneous systems, and we've described the whole set parametrically. And that process is exactly what we need to do to find the basis. And I'll just remind you, I'll use the same matrix I'll say in the matrix and find the basis for the null space now. To find the null space, I would generally put an extra column of zeros in and do the reduced row echelon form of that, because that would be the augmented matrix for the system, AX equals 0. Right? But the process of reduced row echeloning this thing is not dependent on that last column. That's just all zeros, and that last column will just come along for the ride. So in a way, I could have just looked at the same reduced row echelon form here, because that's the first 5 columns that I have there. Right? But what we did in the past is we said, hey, I've got 2 leading ones, and then I've got 1, 2, 3 columns that correspond to free variables. So I let those be parameters, x2, so corresponding to the second column is parameter r, x4, the fourth column is s, and x5, t. And then I can see that this solving for x1, so I'm going to have x1 plus 6, x2 plus 4x4 plus 5x5 equals 0, and so slide everything over to the other side, and x1 is minus 6x2 minus 4x4 minus 5x5. And then likewise, x3 is going to be minus 2x4 minus 3x5 when you move those over to the other side of the equation. Okay. Then what we generally did was we said, okay, x1, 2, 3, 4, 5, those components are equal to, and I just wrote the things in here. This was the formula for x1, x2, x3, x4, and x5. And then I can split this up. I've got 3 parameters, r, s, and t, so I'm going to split it up into the sum of 3 vectors, one that has all the stuff with r's, the second one all the stuff with s's, and the third one with t's. So I see a negative 6r up here, an r in the second position, and those are the only ones. So this is r times negative 6, 1, 0, 0, 0. Likewise, there's an s in the first spot, nothing, s in the in the third and the fourth spots. Right? So in the first spot, s is multiplied by negative 4, in the third spot it's multiplied by negative 2, and in the fourth spot it's multiplied by 1. So I have this vector minus 4, 0, minus 2, 1, 0 times s. And then lastly, the t's, I see a minus 5t in the first position, a minus 3t in the third position, and a t in the fifth position. So minus 5, 0, minus 3, 0, 1, all times t. What we said before was that this is describing all of the solutions to that homogeneous system. Well, now I can see this as in a different way, because what I'm doing is I'm taking a linear combination of these 3 vectors, right, multiplying each one by a constant and adding them up. The solution space to this homogeneous system is the span of these 3 vectors. The question is, are these 3 vectors linearly independent? And the answer is yes, they are. And it may take a little bit of work, but because of the 1, 0, 0, 0 here, the 1, 0, and the 1 in those 3 columns, that there's no way that you can get a linear combination of these 2, the first 2, to equal the third one, or vice versa, right? That no one of those is a linear combination of the other ones. So they're linearly independent, they span the solution set, and so they are a basis for the null space. It's the same process we did before, we just have a different way of talking about it. And the theorem that we'll end with here is just that this works in general. It's not just the one we did, but if R is a matrix in row echelon form, then the rows of the leading ones form a basis. So the rows with leading ones form a basis for the row space. And more so, the columns with leading ones form a basis for the column space. Now, they don't form a basis for the column space of the original matrix, but they form a basis for the column space of this one. Right? This reduced row echelon form, these two rows were columns for the basis for the row space. It turns out that these two columns are a basis for the column space of this, not of that. We'll have to talk about that in the next video. But row echelon form is going to be nice for us to identify independent rows and independent columns. We will look at the column space in the next video.